Here's something I have not discussed.
You did go over this where you did it for the exam.
You just did one. You just
I just
one.
went one.
Yeah.
Let's talk about it again. This is so important. I can define dy dx or y prime. I should look at my definition of a derivative. And as h goes to 0, let's take a peek at f of x plus h. Minus f of x all over h, which in this case is nothing more than a limit. As h goes to 0, the inverse sine of x plus h minus the inverse sine of x all over h. But this is, what's that?
On your,
Oh, thank you very much. I appreciate that. So, be honest with me, guys. Do you remember the addition angle identities for the inverse sine function?
you know that?
Is that the sign?
Let me rephrase that. Do you guys remember the addition angle identity for the inverse sine function?
No.
When did the sine function? What about the inverse sine?
That's not the inverse.
Thank you. Did you guys see my point? We didn't have any addition angle identities for the inverse sine function.
It's for the regular sine function, right?
Just for the sine and cosine and tangent. So I think I'm 100% completely out of luck. I can't do it. This looks way too sophisticated, so I'm going to cheat. I'm going to be really lazy.
Are there actually
No.
no?
That's my point. You don't have anything with trigonometry that allows you to deal with the inverse sine of the sum of two angles. I got a better idea. Don't change what's above this squiggly line. Let's let y equal the inverse sine of x. Let's find dy dx, but check this out. If y is equal to the inverse sine of x, and I can't deal with the inverse sine of the sum of two different terms on the inside, let's just get rid of the inverse sine function. Let's take the sine of both sides. Isn't that statement equivalent to this one? And maybe since you and I have implicit differentiation under our belt, get right.
I was just gonna kind of clarify. I haven't done the inverses in a while. Okay, one it's the one where it's like flipped over the origin, right?
Flipped over the line y equals x.
So like, yeah, that would be like that.
Yes, exactly. So Ryan, check this out. Watch. Let me review just a tad bit of trigonometry. If this is the graph of y equals sine of x, I think geometrically speaking, to generate the graph of this equation, all I need to do is talk about the graph of this equation and reflect that black image through the line y equals x. And I think here's what I get. So this should be the graph of the inverse sine function. Are you guys happy?
No.
What do you know? Why not?
Because the domain is restricted.
Why?
It's because you need a function.
I don't want to. I like it this way. What's wrong with this? Nibio, what did you just say?
We need a function. Fails the vertical line.
Thank you. I think everything I'm doing on the board has to be horribly wrong. You look at the red image. Doesn't that fail the vertical line test miserably? So I guess the bottom line is when it comes to that black curve, there is no inverse sine function. There really isn't. However, if I just for a brief moment restrict the domain of the original sine function, maybe from, I don't know, how about negative pi halves to positive pi halves? Not only do I have a one-to-one portion of the original black sine wave, but it spans all y values from -1 to +1. And so if I restrict the domain of the original sine function for values of x to be from negative pi halves to positive pi halves, I think when I reflect that image through the line y equals x, you check out what I generate. I generate a red beast that really is a function itself. I will refer to that red beast as a graph of the inverse sine function if I restrict the original sine function from the interval from negative pi halves to positive pi halves.
And then my other thing, was the inverse the one where you can just switch x and y? And then
That's exactly what's going on.
Okay.
I agree completely.
Okay.
That's why it's a reflection from line y equals x.
How do we distinguish between sine x to the power of -1?
Hugely. You know,
Well, how do we distinguish
We're not
like
gonna have
with
to
notations?
that's a really good question. If I really meant to raise the sine of x to the -1 power, I'd have to write it as such.
Oh, so like that's the one time when we raise the trig function to
Yeah.
the power.
Yeah, as a matter of fact, if I really did raise the sine of x to the -1 power, did you get something more convenient to write?
1 over sine x.
Say it again.
Oh,
Cosecant.
Very nice.
Okay, gotcha.
And Nabil, for this reason, because the ambiguity of notation, some people never write sin superscript -1. Some people instead choose to write it as the arc sine. Whoops, I can spell arc. I really can. Arc sine of x instead, so there's no confusion with the ambiguity of notation.
Oh, okay.
Oh no, I never answered my question. What am I trying to find?
Why?
dy dx. And to find dy dx, let's treat y as a function of x and differentiate implicitly with respect to x. And to differentiate the cosine of anything, I misspoke, sorry. To differentiate the sine of anything, I get the cosine of that thing. It's just that since I'm differentiating with respect to x, the chain rule says I multiply by dy dx. Now to differentiate the right-hand side with respect to x, piece of cake. But that means dy dx is just 1 over cosine of y. I have not done anything wrong. I'm happy with what I have in the import. It's just that, if at all possible, it'd be really slick to rewrite this in terms of x. I think I can. Because you guys take a peek at what this mathematical statement right here really says. It says, if I were to embed y as an angle inside a right triangle, then to say that a sine is equal to x really means a sine is going to be the ratio of x to 1, which is a ratio of the opposite side of the hypotenuse. And by the way, since I'm here using the Pythagorean theorem in my back pocket, I guess that means the horizontal leg has this length as an expression of lengths. Oh, shoot. You take a peek, I can rewrite this garbage. I suppose that means dy dx is nothing more than 1 over the cosine of y, but look at my picture. The cosine of y is nothing more than this. Do you guys agree? Oh, while I start a list, how about some whole new differentiation rules? To differentiate with respect to x, the inverse sine of x is simply going to give me 1 over the square root of 1 minus x squared. Or it's understood that x has to be living between, strictly living between -1 and +1. If I were to differentiate with respect to x, the cosine of x, oh, you guys, I'm tired. I'm beating that clock. Can I use a shortcut? No, I heard no. You guys, tell me if this is intuitive or not. Yes, no? I mean, is that immediate in your head or not?
No.
Oh, no. Oh, okay, never mind. Yes or no? I take that back. Don't answer that question. Using your unit circle, is what above my brace an x-coordinate or y-coordinate point? Which one?
Neither.
Neither. It's an
Angle.
angle. I'll give it an angle. This doubly underlined is nothing more than another angle. Question, is that really true? Well, let's draw a picture. Let's talk about alpha. In this pretty picture right here, a right triangle, if this is alpha, to say that alpha is the inverse sine of x, doesn't it mean the sine of alpha is equal to x over 1? What can you say about this angle beta right here? What's this cosine? X over 1. And this is a right triangle, so 90 degrees is being used up. Assuming we're in a Euclidean plane, what must the sum of these two angles be?
9.
Oh, that's exactly what this says. Isn't it? Okay. Of course, if we're not in a Euclidean plane, it's different, but let's just imagine we're in a Euclidean plane. So, help me with this. What's the derivative of this thing? I don't know. I'll call it this. Plus derivative of this. What's the derivative of pi halves?
0.
Oh, wait. What this really says is that derivative of the inverse cosine and derivative of the inverse sine are the same thing. They just have a sign change. S-I-G-N, not S-I-N-E. And so I guess the derivative of cosine, the inverse cosine of x has got to be, well, negative 1 over root stuff. Come on, you guys, isn't that a piece of cake? And if I were to try to differentiate with respect to x, the inverse tangent of x, I don't know, let's go through this argument again. If y equals the inverse tangent of x, doesn't that mean this? But to differentiate with respect to x, the tangent of anything is just secant squared of that thing. Ah, shoot, chain rule. But differentiating with respect to x, the right-hand side just gives me 1. So I think dy dx is nothing more than 1 over the secant squared of y. However, if you guys allow me to take a break and draw a nifty little picture again, a right triangle picture, that depicts that the tangent of some angle y is x over 1, doesn't that mean that? But that means the hypotenuse is the square root of 1 plus x squared. But that necessarily means that when it comes to dy dx, I've got a 1 over secant squared of y, but cheapers, secant of y is just hypotenuse over adjacent. So its square is going to be 1 plus x squared. Wow, look at that. We just differentiated the inverse tangent of x. It's just 1 over 1 plus x squared. Using a similar co-function identity relationship like this, I think to differentiate with respect to x, the inverse cotangent of x is simply going to give me a sign change for the derivative of the inverse tangent of x. I'll leave it for you guys to check the derivative with respect to x. Same argument of the secant of x is going to be 1 over the absolute value of x times the square root of x squared minus 1, where, of course, in absolute values, x has got to be bigger than 1 for that thing to be even defined. And using another co-function identity, that means a different derivative with respect to x of the cosecant. I misspoke. Everybody watch. I miswrote as well. I really made an error. I really meant inverse secant. But using another co-function identity, I think this derivative is just going to give me a sign change. So as of this point, I'm sorry if you don't want to hear this. I need you to know the derivative of these inverse trig functions. But you can always rederive them. Libya?
Is the domain limitation the same for all of them?
No, quite to the contrary. Check this out. Notice how this really means the following. In absolute values, x is strictly less than 1. But here the absolute value of x is strictly bigger than 1.
So is the one on the top applied to sine, cosine, tangent, cosine?
You know what, you're right. I didn't write it, but it certainly is true here. And it's certainly true here. However, for the inverse tangent and inverse cotangent functions, the domain is going to be all real numbers. It's true for all real numbers x. There's no restriction.
Or you said tangent and cotangent?
Inverse tangent and inverse cotangent.
Oh, okay.
No restrictions.
Is that absolute x in the denominator?
Yes. Yes. Am I being too sloppy? Just a little bit. My apologies. Randall.
Can you do the geometric proofs
Of the,
for the rest of them?
you mean the inverse secant?
Yeah.
Absolutely. So you guys check this out. If y is equal to the inverse secant of x, then isn't it the case that y is an angle whose secant is x. But that necessarily means if I were to differentiate both sides with respect to x implicitly, oh shoot, I gotta slow down. To differentiate secant, I get secant of the y times the tangent of that y, but the chain rule says I gotta multiply by. But to differentiate the right-hand side with respect to x, I just get a
1.
So I think, algebraically speaking, dy dx is merely the ratio of 1 to this darn nifty little product. It's just that when it comes to that product, I'm not happy. I haven't done anything wrong. I would just, if at all possible, I'd really like to rewrite this in terms of an expression only involving x, if I can. So I think it's, yet again, you guys watch. It's time to take a break. Let's take that angle y. Let's embed it in a right triangle. However, that angle y has a quality that is secant is x. But doesn't that mean that the ratio of the hypotenuse to the adjacent side is x to 1? Which, by the way, means that the other leg is going to have length x squared minus 1 underneath the square root. It's just that if I were to make some replacements in here, you guys check this out. I think another name for the secant of y is the ratio of x to 1. And another name for the tangent of y is the ratio of opposite side to adjacent side. I think. Shoot. You know what, you guys? I'm nervous. I think sometimes x is positive, sometimes x is negative. I think I need to modify this derivative real quick. But to do that, can I just draw a funky looking picture? All my pictures are funky?
Yeah.
Is that what you say, Krista?
Sorry.
I'm going to remember that when I sign a letter grade your name in the semester.
How can x be negative?
What's that?
I said, how can x be negative?
Oh, what a good question. I'll show you how.
Okay.
Am I okay so far? In my picture, is this a one-to-one function? Is it a one-to-one function?
No.
I don't think it is. Doesn't satisfy the horizontal. I can't speak.
Vertical
Doesn't
line.
satisfy the horizontal line test, and therefore I don't think it's going to have an inverse. I got an idea. Let's use our restrict this domain from 0 to pi. I think with that restriction, not only is that a one-to-one piece of my cosine wave, but it spans all y values from -1 to 1. Holy cow, you guys, I'm talking about the wrong function. I want the secant function. Piece of cake. Secant is just a reciprocal of cosine, so I will reciprocate all the y values. I think with a vertical asymptote at x equals pi halves, this in blue is nothing more than the graph of this equation. Do you guys agree? So for me to now generate the graph of the equation y equals the inverse cosecant of x, let me take all the blue garbage and reflect through that line. And if I reflect all that garbage through the line y equals x, I think in blue, shoot you guys, I'm a little slow, hold on a minute. I think what I generate is this. I may be a little off scale. You guys, I know I can't draw very well, but can you see the picture I have in red, which is nothing more than the graph of this equation? Are you there? Okay, do this for me. If x is 1 or to the right, is the slope of the tangent line at any point going to be positive? Always. See, I think the answer is yes. As long as I'm strictly to the right of 1, I think the slope of the tangent is always going to be a positive number. Slopes are always increasing. Yes or no answer. To the left of -1. For any value of x that's less than -1, is the slope of the tangent line positive?
No.
I agree. It is positive. However, If I plug in negative value for x, this is always positive, but this is negative. So I think if x is negative, I need to change the sign of x. But so that I don't change the sign with positive values of x, I just look at the absolute value of the x. That's why in this differentiation rule over here, I really do have the absolute value bars. Randall, might help me.
Oh, yes.
Okay. Maybe
How come for the inverse sine and inverse cosines, it's not a positive or negative square root? I don't really see why. Because if you like solve it and you work through it, you have to square both sides or square root both sides, and then shouldn't you get a positive or negative?
Ay, ay, ay. What a good question.
dy dx. 1.
Okay, you guys, he's got an excellent point. When I put this garbage on the inkboard before, I cheated. I hand-waved with Harry Potter mathematics. You know, technically speaking, this should be plus or minus the square root of the garbage. It's just that, if you look at the statement very carefully, the output of the inverse sine function is an angle y that only lives between negative pi halves and positive pi halves. And if you look at any angle between negative pi halves and positive pi halves living in the fourth or first quadrant, what's the cosine of any such angle? It's always positive. That's what allows me to make this decision that I only choose the positive component square root. Did you catch that?
Oh, and that's why for inverse cosine of x you choose the negative one?
Actually, yes, it is.
Okay. So, you solve or you derive inverse sine of x and inverse cosine of x the same way. It's just that. For
You know,
inverse
I
cosine
admit,
of x-
Nabil, I just cheated to save myself some work. I actually, to get the derivative of the inverse cosine of x, I exploited this relationship.
Okay.
I did that instead. I differentiated both sides and I saw that inverse sine and inverse cosine have to have opposite signs. SIGN.
Okay.
I cheated. I didn't go through all the work.
Can you explain how you drew the graph or the cusp, I guess it's y equals secant of x, can you explain how you drew the cusp that came down and up?
You mean this portion right here in red?
No, in blue,
Down to the
black
right.
and blue, yeah.
Gotcha, right here.
And on the other side too.
Gotcha. First, before I do that, could you go back to black? And I know I don't draw very well, but what I have in black is a restriction of the cosine away from 0 to pi. It's just that when it comes to blue, watch, check this out. Isn't this blue garbage? Interpreted as this used by reciprocal identities in trigonometry. And so I think to graph the blue garbage, I would just take the y values on the cosine function in black and reciprocate its y values. Watch me do this. I think this y value is positive 1, but 1 over 1 is.
1.
But I think the y value over here in black is less than 1. So 1 divided by something smaller than 1 is bigger than 1.
Okay.
And the closer and closer my y values in black get to 0, the larger and larger the y values get on the blue curve, which means when x is equal to 0, when the black curve crosses the x-axis, I got a vertical asymptote. So you see it?
Thank you.
You're welcome. Right. So Brett went overdue. I'm so sorry. So you guys are tired of hearing me talk. Let's take 10 minutes.